Okay. So someone asked what is gradient. Okay, so now you are having a function from D to R where D is a domain in Rn. Now what is gradient? Gradient is nothing but the, so if you are, suppose let us say if your domain for example is R3, right? If your domain is R3, then what will you do? You, for finding the gradient of F, you write what is partial derivative with respect to X, partial derivative with respect to Y, partial derivative with respect to Z, right? So for Rn, you know it is going to be fx1, x2 up to fxn. So we are finding partial derivative with respect to each variable and then writing them as a vector. So that is what is a gradient of a function. Okay.
Uh, Ma'am,
Yeah.
you actually, you know, like as we study slope, it's like change of y-axis with respect to x-axis or something.
Yes. Yes.
But it's and the way you define gradient is just a formula. I'm just I'm trying to know why we need gradient. Like once I saw a video of three blue and one brown channel, they people says like they relate with fluid or something. I don't know why.
They related with what?
Fluid dynamics. They in physics perspective.
I don't know what is exactly dealt there. See, what is rate of change in our case? If you see, rate of change is nothing but directional derivative is what we talk it as rate of change. And in terms of one variable function,
Yes, ma'am.
rate of change is nothing but the derivative, right? So, whatever you are saying, this change in y by change in x, that limit only gives you the derivative in case of one variable, right? Yes.
Yeah, yeah.
So here also in this week 10, we are going to see that how this directional derivative is going to contribute to something similar to what we have seen in the case of one variable, like positive slope, negative slope, all those things you have seen about derivatives, right? So we will see
Mm-hmm.
similar concepts today. So maybe at that time we will discuss further on that topic. Okay, fine. So directional derivative, this is a precursor for that. So if the gradient of the function exist, so you need all the partial derivative first of all to exist, and if this is a continuous function, then only the directional derivative will exist. Okay, and directional derivative is the rate of change. Okay,
Yes, ma'am.
fine. Okay, so here you see that we have a function. Okay, so now this function approaches a limit L as x tends to this point A. Okay, similarly, just similar to one variable function, then limit x goes to A, f of x is equal to L. Okay, so here you see that the limit of f at A tilde exists and equals L precisely when for every curve in the domain D passing through A, the limit of f at A along C exists and equal to L. I guess if you remember, we have seen that. So in case of one variable functions, we look at the left hand limit and right hand limit of a function. Suppose this is some function and this is your point A, then x goes to A plus and f goes to A minus. This is what you see for limit, the existence of the limit at A. In case of multivariable function, here what we are looking at, instead of just right and left, here we have to look for every curve in the domain D passing through A tilde. Okay, so the limit of f at A tilde along C exists and equals to L if for every curve C in the domain passing through A, the limit of f at A exists, and it should be equal to L. Okay, it is not enough if it just exists. For example, you see that here the limit exists from both the directions, but they are different. So if they are different, then it cannot exist, right? So the same concept here it goes. Mainly this theorem we use when we are trying to prove that the function's limit does not exist. Okay, this theorem is used mainly to prove that the function limit does not exist. In that case, you find, so to show that the limit of f at some point does not exist, so either you produce a curve where the limit does not exist, or you produce two curves where the limits are different. Okay, so this is many problems we have seen to understand this. And the next concept is the limit of a vector valued function. So for vector valued functions only, here instead of just one function, you will be having several functions like f1, f2. You will be having several functions. Okay, so you are having here, for example, maybe n. here I guess k functions. Okay, so you are having k functions. Okay, and each of this f1, f2, fn, these are now functions, the usual one variable functions. Okay, and here you see that if fi is the ith component of the function f, then fi is a scalar valued function from d to r. Okay, so here fy is also a function from d to r only they are saying. Okay, so in that case, what we are doing, we have already defined what is the limit in those cases. So now we are going to use that limit formula for each of these functions, and we are going to find the individual limits. So that limit written as a vector is the limit of this vector valued function. Okay, and we have also solved examples for the similar type. Okay, and then we saw what is continuity of a function. We saw that for continuity, if you split the definition, then we have three things to check. First thing, you need to check whether f is defined at a. If it is not defined, then no need to check anything. Defined at a or a tilde in this case maybe. Okay, and then limit x goes to a tilde, f of x should exist. And the third condition is that, what is the third condition? Can you tell? It is there on the screen itself. This should be equal to what?
At a point.
What is that point? A tilde. Okay. So if all these conditions are satisfied, then we say that f is continuous at the point A tilde. Okay, so if a function is continuous at a point, then the limit at a can be obtained by evaluating the function at a. That's why whenever we have some polynomials or maybe trigonometric functions, we know that if the function is defined at a and then it is continuous, so we simply substitute the value of a in the place of the variable, right? Okay, so here, yeah, gradient vector or function, I have already explained it to you. So this is the gradient vector. Okay, and you see that directional derivatives can be found in terms of the gradient. So you see that the directional derivative along the unit vector, uh, along the unit vector in the direction of v at the point a tilde is given by the gradient of f at a tilde dot product with the unit vector in the direction v. What is the unit vector in the direction of v? It is nothing but v by norm v. Okay, so if you are given any vector and asked to find what is the unit vector in that direction of that vector, how will you find? Simply do v by norm v. Okay, fine. So these are the things we have already seen. Now let us quickly recall what is slope. Do you remember what is slope? Yeah.
Yes.
Okay. So if you are given 2 points x1, y1 and x2, y2 on a line, right? So you are given 2 points on a line. Then how do you find the slope? This is the formula for slope. y2 minus y1 by x2 minus x1. So this is the change in y. y2 minus y1 is the change in y, and this is the change in x, right? So now, for example, if you are considering a line like this or line like this, what is that you observe? In general, if you are taking any point here and then a point somewhere here, what can you say about x1 and x2? What is the relation between x1 and x2? x1,
X1 is less than X2.
yes. So this means that x2 minus x1 is
Positive.
positive. Now, for this particular graph, suppose you are taking any 2 points on this line. Okay, suppose you are taking any 2 points on this line. Okay, what will, and this one, let us say this is x1 y1, and let us say the one on the right hand side is x2 y2. Now what can you say about y1 and y2?
Y2 is greater than Y1.
Yes, so in that case y2 minus y1 is,
Greater than 0.
yes. So in this case, what will happen to the slope? You see that the numerator as well as the denominator both are positive. So what will happen to the slope? The slope is also
Positive.
Positive slope.
positive, right? Now here in this example, suppose you are taking 1 point here, call it x1 y1, you take another point x1 y1, x2 y2. Now here also you know that x1 is less than x2, that is as a standard thing for all these three graphs. But what about y1 and y2? What is the relation?
y1 is greater than y2.
Y1 is greater than y2. See, along the y-axis, this is on the top and y2 is below it, right? So y1 is greater than y2. This means that your y2 minus y1 is less than,
Negative, yeah.
right? So it means your slope is also
Negative.
negative, right? Now consider this graph. Here, let us take any point x1, y1 here and another point x2, y2. Okay. Now, what can you say about y1 and y2?
Both are equal.
Both are equal, right? So in this case, what can you say about the slope? Now, y2 minus y1 is
0.
0. So the slope is 0,
0.
right? So you see that when generally you go upwards like this, right? You have a positive slope, okay? And then when you are kind of in a horizontal space, right, you have 0 slope. It's not necessarily something like a line. Even when you have, yeah, let us see maybe later on. This is what you should understand. For any horizontal line, the slope is 0, okay? And negative slope means downward. If the direction is downward, then the slope is negative, okay? So you can easily understand from this graph that for 0 slope, you don't have to make any change in your effort. So you simply walk. But where is the effort? More effort is needed. Positive slope, 0 slope, or negative slope. When you're moving on a mountain, where do you need to put more effort?
Positive slope.
Positive slope.
So, and where you need very less effort?
Negative slope.
Negative slope.
Negative slope, right? Okay. So here you see that these are the concepts we have already seen. Now let us see how we are going to see the same concept in multivariable function. Now the topic is the direction of steepest ascent and descent. First of all, what is ascent and descent? Ascent is nothing but upward movement and descent is nothing but downward movement. Okay. What is derivative in terms of slope? So derivative is the slope of the line tangent to the curve at a given point. So in terms of one variable calculus, if you remember the derivative, if you have any function, then what is the derivative of the function at a given point? It is the slope of the tangent line. So you take the tangent line and the slope of the tangent line at that point is called the derivative of that function at that point, right? So the ascent or descent of a curve at a point is determined by the derivative at the point, correct? Because here if the slope is positive, will you have an ascent or descent?
As
Ascent.
Right? So the derivative is nothing but the slope, right? So if the derivative is positive, you will have ascent. And if the derivative is negative, you will have
descent.
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 And if the derivative is 0, it means that you are having no rate of change. So it is going to be some horizontal surface, right? So this is what you see in one variable. So same concept. Let's see how it works here. So you are considering a problem here, which is tracing water flowing down a hill. Okay. So for an electrification project, Mohan Bhargava is trying to understand how water flows down a particular hill. By the way, is this name familiar to anyone? Not this exact same name, but this Bhargava.
Yes, ma'am. Manjul Bhargava, the field
Yes,
medalist.
ma'am.
Yes, right. Manju Bhargava, everyone should know. He is
Yes,
an
ma'am.
Indian who got field medalist, right? The highest prize for mathematics. All right. Anyway, continuing back. Okay. For an electrification project, Mohan Bhargava is trying to understand how water flows down a particular hill. How does water flow downhill? It will move in the direction. Someone should mute. Okay. So how does water flow downhill? It will move in the direction where the altitude decreases most rapidly. Is that correct? Yeah. So when the altitude decreases most rapidly, that is where the water will flow downhill, right? So here it will, so from here you see, from this point, it will flow down here. From this point, it will flow down to this side, right? So these are the places where you can see that the water will flow downhill, right? Now Mohan models the hill as in the previous picture using the graph of the function h of x, where h is the altitude of a point. He then calculates the derivative h dash of x and computes at which points it is negative, positive, and zero, right? So we have already seen if the direction, if the derivative is negative, then you know that we will have ascent or descent.
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 Water flows to the right, right? So you look at this picture. When you have a descent, so when you have, for example, a negative slope, so in these places you will have a negative slope, right? So in these places you are having a negative slope. So if it is having a negative slope, then the water is flowing in which direction? To the right from that point, right? It is flowing to the right from that point. Now, if you are considering water flow in the other direction, so you are considering the slopes like this. So now where will the water flow for these places? It will flow towards which direction? Here you see the slope is positive. For this line, the slope is positive. This line also the slope is positive. Here also positive. So in these cases, water is flowing towards which direction? To the
Downwards.
left. Downwards in both the cases. From this point, it is going downwards here as well as here. But when the slope is negative, it is going to flow towards right. And when the slope is positive, it is going to flow to the left side. That is what you should understand for this problem. Is that clear?
Yes.
Ma'am,
Yes, ma'am.
how this slope is negative? Actually, on right side, yeah, this
Yes.
is.
Yes. You are asking how?
How the slope? You said negative slope, right?
Yes.
Like the angle is less than between 0 to 90.
Sorry, what is that you are saying? See, look at
Why?
this picture here. Any line I said, like this, like this, like this, where your y1 value is greater than y2, so in all those cases you are going to have negative slope, right? So now you take any 2 points maybe here and look at the difference between y1 and y2. They are negative, right, in all these cases. So it means they are negative slope, right?
Yes, ma'am.
The
Okay.
same you see for the blue lines. You take any 2 points on the blue line, you see that the difference is positive, so you are having positive slope. Okay,
Oh, yes,
fine.
ma'am.
So for negative slope, the water is going towards right, and for positive slope, the water is going towards left. Okay, this is what he observes. But then Mohan's friend Geeta points out that a one-dimensional model will not be useful, right? Because it is just going to be some cross section, right? It is going to be the intersection of the original picture with the plane. Okay, what is actually needed is a two-dimensional function h of x comma y to model the altitude h. So to model the mountain, you need a two-dimensional function. So she is considering h of x comma y, right? Now when we are having h of x comma y, so which will give you the rate of change?
H dash of x comma y.
No, for functions of several variables in place of derivatives for rate of change, what is the term? Even in today's lecture, I told you.
Gradient.
Not gradient,
Directional
directional,
derivative.
right? Yeah. So now you see that Geeta tells Mohan that water flow in the direction in which the altitude decrease the fastest. That is along the steepest slope downward. So now our task is to find how to find the steepest slope downward, right? She says that to compute it, we have to find the direction in which the function h decreases fastest, or equivalently, the rate of decrease of h is fastest, right? So what it is equivalent to mathematically, this is same as finding the vector u in which the directional derivative hu is largest in absolute value amongst those for which it has negative sign. For example, let me just give you few numbers. Okay. Now, out of these numbers, which one is having highest absolute value?
Ma'am, minus 5, 6, and oh, highest.
Minus
1,
Ma'am,
Highest
7,
value.
minus 7.
7.
Just look at this carefully. Which number is having the largest absolute value?
Minus
Ma'am,
17.
12.
Minus
Yes.
17.
17.
So you see that this
17.
is the one which is having the largest absolute value, right? And it is negative, right? So what is that you need to do? You need to find that the directional derivative HU is less than or equal to HV for all V in R2, right? So you, for example, you see that this value is less than all other values, right? So in this case, but here you have to look for all the vectors in R2, and then it should also be negative, right? So either you can put it as the one which is having largest absolute value with negative sign, or you can say that HU is less equal to HV for all V in R2 and HU is less than 0. So your directional derivative should be the smallest. For that, you will get the steepest slope downward. Okay, is that clear?
Yes,
why
ma'am.
why we have this directional derivative with these conditions to get the steepest slope downward? Do you understand that, everyone?
Ma'am, can you please explain this part again?
Okay, let me just maybe give you the picture in terms of 1D, maybe then you can understand it better. See what happens when you have, maybe let me draw a function. So here you see, let us say you are having a graph like this. Okay, so now let us maybe consider few points. This is A, this is B, this is C, this is D, maybe C I will put somewhere. Right? I'll put the graph like this and C is some point here. So D is here and E is here. Okay. Now, can you tell me at which point you will have a positive slope?
A and D.
A
A,
and D.
A and D are going to have positive slope, right? Now, which points will have a negative slope?
C, E.
C, E.
C, E. Okay. Now, imagine that this is a mountain. Which area is having more slope, or in terms of mathematical terms also, which compared to C and E, when coming downhill, which one is having more steep, more slope, where it is more steep, C or E?
E.
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 Right? E, right? So you notice that it at E you have the steepest descent. Do you understand?
Yes,
Yes.
ma'am.
So this is the place where you have the smallest derivative among other points with negative sign. Do you understand?
Yes, ma'am.
Now that is the same thing we are looking here also. You want to find the direction where you have steepest slope downward. So for that, you are going to consider the directional derivative, which is the smallest with negative sign. Now is that okay? Clear?
Yes, ma'am.
Ma'am,
Yes.
at point B you say negative slope, right? Negative differentiation, right?
Not negative differentiation, negative slope. Yeah.
Ma'am, then
Okay.
what is this HV
This is the
comparing?
directional derivative. See, instead of just derivative, here you are talking about derivatives. Now, instead of derivatives, when we are having a multivariable function, you are going to have directional derivative when you have to talk about rate of change. That's all. Here, this HU is the H is your function and HU is the directional derivative in the direction of U.
Ma'am, but there can be a situation in which we can reverse U and V, like HV can be less than HU and HV
That is,
can
that is what I'm saying. You are going to find the steepest slope. Steepest slope in the sense no other point should have a slope bigger than this. So that is why for comparing to all other places, You are finding a point where the directional derivative is smallest. So that place the slope is steepest. Okay, got it?
But
Yeah.
why are we trying to find the steepest slope?
Because that is where the water flow is going to be fastest. Correct? When the slope is steepest, the water is going to flow fast. Correct? Yeah,
Yes, ma'am.
that is why. Okay, fine. So now let us before going to the problems, now let us see some more things here. Now, in what direction is the directional derivative minimized? Now we are going to look into the process of finding the directional derivative where it is minimized. Okay, so now let f of x1 x2 xn be a function defined on a domain D in Rn. Okay, so now D is a subset of Rn and A tilde is a point in D. Okay, now you are going to consider a open ball around the point A tilde. Suppose del F exists and is continuous on some open ball around A tilde. Why are we considering this condition here? This guarantees the existence of what?
Derivatives.
Directional derivative.
Derivatives.
Yeah, it's correct only. Directional derivative. Okay, so that's why we are assuming this this condition. Okay, so now just quickly recall, do you recognize this as a function of cos theta? Yes.
Yes.
Yes,
What
ma'am.
is the highest value for cos theta?
1.
+1.
Right. So now between 0 to 2 pi, where do you get the highest value?
1.
No, what is the highest value is 1. Where do you get the
0.
highest value?
0.
0.
Right.
0.
So highest value is when theta is 0. And what is the value?
1.
1.
So cos theta is 1 there. Now what about the lowest value?
Minus
Minus
at pi.
Minus 1. And where does it occur?
Pi.
Yes. When the value is pi, you get minus 1. All right. Now, where is the value 0?
90 degree. Pi by 2.
Right? Here, if you consider 0 to pi, it is at pi by 2. If you consider the entire range, then you consider pi by 2. So, here we are considering 0 to pi. So, mainly we are talking about pi by 2. So, pi by 2 and then cos theta is 0. Right? So, these are some observations which we are going to use now. Okay, fine. Now, do you remember dot products we have seen?
Yes, ma'am.
What is u dot v in terms of norm? If you expand, how can you expand? Does anyone remember? So let us say
Let
you have two vectors u and v. How do you write u dot v?
Norm of u into
Norm of u into norm of
norm of V.
Norm of V.
cos theta.
Cos
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 theta.
cos theta. And what is theta?
Cos
Angle.
inverse u dot v dot
Angle
no,
between.
divided by the norms.
No, theta is just the angle between u and v. That is what I was
UNV.
asking. Okay, fine. So now with this definition, now let us look at what is the directional derivative. Do you remember how we wrote directional derivative?
F
We
of
can,
a plus tu minus f of a upon t. T tending to 0.
so the gradient into,
Directional vector dot u.
right? So this is in terms of the gradient I'm asking. So now let us use the same formula here. So if I'm using the same formula here, and cos theta, you know that theta is the angle between,
Both the vectors.
yes, it is the angle between the gradient and the unit vector, right? Now what is norm u? You know that u is a
Unit vector.
Unit
If u is
vector.
a unit vector, then what is norm u?
1.
1.
Right? Norm u is 1. It means that your directional derivative at a tilde is nothing but gradient of f at a tilde, norm of gradient at a tilde into cos theta. Right? Now, once you know this value, now this is a number. Right? So now depending on your u, your theta will change. Right? Your theta depends on u. Correct? Your a is fixed, your f is fixed. You need to find what is the direction of steepest descent. Now, theta varies depending on you. Yes or no?
Yes.
Yes, ma'am.
The other part is fixed. This part is fixed for you. So your theta varies depending on you. Right? So now, when will you have, maybe I'll write, minimum value of fu of a tilde is attained when theta is equal to, from the above information, can you tell when theta is equal to
Pi
which
by
value?
2.
See, your this value should be minimum. When is it going to be minimum?
Pi.
Right? When it is pi. Right? If it is pi, what does that mean?
Then cos
Minus
theta
1.
will -1.
If it is
Both
pi,
are in opposite
means
direction.
that if it is pi, it means that if this is the direction of your gradient vector, gradient function at a tilde, then your u is going to be just opposite, in the opposite direction, right? 180 degrees, right? So u is equal to minus del f at a tilde by norm del f at a tilde, and fu. Why I'm writing this? Do you understand?
Ma'am, no, so we are ma'am. Finding out the unit vector through the gradients.
Direction, yes, the direction in which, see, your u is just in the opposite direction. It means what? So your u is a unit vector in the opposite direction. It means it is along the same line as del f of a tilde, but in the opposite direction. That's why a negative sign, and it is a unit vector, so I am dividing by its norm. Do you understand now?
Yes, ma'am.
Okay. So did you all understand, or should I repeat? How
No,
did
no,
I
no.
write this u?
Understood. Understood.
Okay, fine.
Got it.
Now, what is fu of a tilde in this case when theta is equal to pi? Cos.
Minus
Minus
of
times.
the norm.
So your
Um,
cos theta is minus
0
1.
by -1. So
So it is minus norm
norm.
del
Of
f of,
F A
okay,
tilde.
you understand? So this is for the minimum value of fu of a tilde. Okay. Now the maximum value of fu of a tilde. When is this attained?
at theta equal to 0.
Right? What does that mean? What does
U
that mean? If
in
this
the
is
Both
your,
are in
direction
the
of
same direction.
delta.
so if this is your del f of a tilde, your u is either smaller or bigger in the same direction. Both are in the same direction, right? So u and del f of a tilde are in the same direction. So how can you write u?
Del
Norm.
of f
Theta of
a
norm.
tilde upon, well, norm of f of a tilde.
Correct? Okay.
Yes.
Now fu at a tilde should be equal to,
Norm of itself.
right? Okay. Now when does fu of a remain unchanged?
When both are perpendicular.
Yes, when theta is pi by 2. So when both are perpendicular. So your u and del f of a tilde are orthogonal or perpendicular to each other. right? In this scenario, you see that it is the FU of A tilde remains unchanged. So what is the value of FU of A tilde in that case? Yes?
Going to be 0.
Yes, it is going to be 0. Right? So far, did you understand what we have done? So we considered one particular example to understand how this rate of change, that is the directional derivatives part, is used. So for that, to understand where the directional derivative increases fast, decreases fast, or remain unchanged, we understood through this mathematical concept. Here we see that in this direction of u, it is obtaining the minimum value. In this direction of u, it is obtaining the maximum value. And in this direction, it is obtaining the small, it is not undergoing any change. Right? So when it is orthogonal. Okay. So far, if it, is it clear to everyone?
So
Yeah?
is it like basically in case of when theta is equal to pi by 2, it's basically like the intention is to go in one direction, but it goes continuously in the perpendicular direction, right?
We are not talking about the function's direction here. See, what is the direction of this gradient vector is what we are talking. That you are not going to visualize. What you are going to visualize is f only. Just for this problem, this is what you are looking at. This you are not going to visualize. Only you have the graph of f.
No, I mean I'm just trying to visualize the like how the just the level slope is being indicated, like the level ground. Like how is it being visualized? Because it is actually similar uh, to the third case, basically level slope.
Okay, you are talking about one variable functions. How we are going to match this concept there? That is what you are asking, right?
No. What I'm trying to say that there's positive slope, negative slope. I'm talking about a case of zero slope, basically.
Yes, that is what I'm asking. So you are asking about zeros, comparing zero slope to one variable case. Is that what you are asking, or you are asking
Like
something?
how can we can we visualize this to the third case that if you remains unchanged?
See, what is happening in the case of one variable, you can easily understand in the case of one variable. Suppose you are having a graph like this. So at this peak point, what is the derivative at this peak point?
0.
0, right? So here your derivative is 0. So the slope is 0. The same thing is happening for this function at this point.
Yes, ma'am.
Okay, fine.
Yes.
Okay, so now summarizing what we have seen. So when will you have steepest ascent? If you have fu is positive and maximum, and this is the direction. And when will you have steepest descent? When fu is negative and minimum. Okay, and it is in this direction of u. And when will you have no change? When fu is 0. Okay, so in this case, u is orthogonal to del f. Okay, so now let us do some problems applying this concept here. So this table is exactly what we need to do these problems. For the following functions, find the direction of the steepest ascent, descent, and the direction in which the function remains the same. So what is the first thing we need to find? Del f, right? You need to find the
Yes.
vector u. So you need to find what is del f. So let us find what is del f. What is del f for this function? Yeah,
Cos xy.
is it y cos xy or just x cos xy?
Partial differentiation with respect to x, it will be y cos xy.
Yeah, y cos xy, comma,
X cos
Cos
xy.
xy.
right? Now, what is del f at pi comma 1? Just substitute x in terms of x pi and in terms of y 1. So here y is 1. So you
Minus
can
y
solve
minus
for
x.
minus 1,
Y.
But
minus 1, right?
yes, ma'am. Yes.
Yes.
Minus 1 and then minus pi. Correct? Now what is norm del f at pi comma 1? Square root of,
Pi square plus 1.
yeah. Okay. Now what is the direction of steepest ascent? Yes.
Del f divided by its norm.
Okay. Fine. Now what is the direction of steepest descent?
1
Just
comma
opposite.
pi divided by norm.
The negative of this vector. Right. Now what is the direction in which direction where f remains same?
U is equal to 0.
So you have to find u. You don't know what is u. U is a vector orthogonal to this vector. That's all you know, right? So let us find that u. So let us call maybe your u as u1, u2. Okay, here we are in two dimensions. So u1 comma u2. Now what is that you know? This u is perpendicular to this vector del f
Del f.
at pi comma 1. So this means that
Dot product 0.
u1 u2 dot product with minus 1 minus pi is 0. What does this mean? Minus u1 minus
Minus pi u2 is
is,
0.
so this means that your u1 is equal to minus pi u2. Correct?
Yes.
So now what is the unit vector in this direction? What is the unit vector in this direction? How will you find? Suppose I am taking u2 is equal to 1. If u2 is equal to 1, then what is the value of u1?
Minus pi
Minus pi.
Minus pi. So now what is the unit vector in this direction? Minus pi comma 1?
upon 1
Upon
root under
x.
1 plus pi square.
Exactly. Right? So your u is nothing but minus pi comma 1 by root of 1 plus pi square. You understand how we got this u? So for the direction in which f remains same, you need to find the vector which is orthogonal to this vector. Is that fine?
Ma'am, can you explain the second last step that you did, wherein you took the value of u2? Yeah.
See, now this is u1 is equal to minus pi u2. So now you know what is the relation between u1 and u2. Okay. So this is maybe something like x is equal to minus pi y. This is the line. Now you need to find the unit vector in this line. So I am taking just any vector. So maybe I am taking y is equal to 1 u1. So in that case, u1 is minus pi. So from this, I am finding what is the unit vector in this line.
Okay,
You
ma'am, got it.
oh.
So we are finding the unit vector. That is why we have taken the value of u2 as 1, right?
No, not. We are
So
first
randomly,
finding just random vector on this line. And then for making it as a unit vector, we are dividing by its norm.
so if we take some other value for u2, that will also work, right?
Yes, it will work.
Okay.
You have to find u1 for that particular u2 you are using. That's all.
Okay, ma'am, got it.
Okay, fine. All right. So don't take it to be 0. Use some non-zero values. That's all.
Yes, ma'am, yes.
Okay, fine. So this problem, all of you understood? Yes?
Yes, ma'am.
Yes, ma'am.
Okay. Okay. So let us do a similar problem for function of 3 variable. Okay, so it is going to be very similar. What is the first step?
Differentiate with respect to their respective variables.
So what is that?
2x, 2y, 2z.
Okay. Now I did not write the point. So the point is at 1 comma 1 comma 1. Okay. So now what is del f at 1 comma 1 comma 1?
2 comma 2 comma 2.
And what is the norm of this vector?
Root 12.
Yes. So we can write it as 2 root 3. Okay. So now what is the direction of steepest ascent?
1
1
comma
upon
root
root 3.
3,
Root.
comma 1 comma root 3, 1 comma root 3.
Yeah. So 1 comma 1 comma 1 by root 3. Right? Okay. Now what is the direction of steepest descent?
Negative of it.
Yes. The negative of the above vector. Okay. Now what is the direction where f remains same?
U equal to 0.
No, don't say u equal to 0 again. You have to find the vector u such that it is perpendicular to del f of 1 comma 1 comma 1, right? So in this case, your u is u1, u2, u3. So now u1, u2, u3 dot product with 2 comma 2 comma 2 comma 2 is equal to 0 gives you u1
Plus U2 plus U3 is equal to
3.
0.
So 2 times of this is actually equal to 0. So this value itself is 0. Correct? All of you are following?
Yes, ma'am.
Yes.
U3 is 0. Right? Now in R3, what does this represent? In terms of U1, U2, U3, imagine X, Y, Z. What does it represent in R3?
So plane.
A plane equation.
This is the equation of a plane, right? So now
Yes,
how
ma'am.
will you identify a plane? For a line, you can easily identify with one vector. Now for a plane, how many points you need to identify a plane?
2.
2 points, right? So let's say this is u1, this is u2, and your u3 is nothing but minus u1
0.
minus u2, right? So in the first case, maybe I am taking your u to be u1 is 1 and u2 is 0. This is how we usually do in finding bases, if you remember. Do you remember
Yes, yes,
this
ma'am.
one?
Yes, ma'am.
Yes,
Yes.
ma'am.
Yes. So this is 1
Basic
by
thing.
1, and the other maybe u, and maybe v, maybe I'll write.
1 comma 1 comma minus 2.
Yeah. 1 comma 1 comma minus 2. Yes, that is another way of doing. But usual thing what we do is we take 0 1, right? This is the usual way we do. Yeah, of course 1 comma 1 comma minus 2 is also correct. So this is u and v. What are the norm of these vectors? Root 2,
Root 2.
right? So these are the unit vectors. Okay, so these are the unit vectors in which, so along these directions, you can see that f is going to remain the same. Okay, fine. So can we always find the steepest ascent or steepest descent of any function at a given point?
Yes, ma'am.
I think
What?
it should del f should
Except
be
if
exact.
it's like a constant slope. It won't happen in two variables.
Yeah, there you can at least say that there is no steepest ascent or steepest descent. But if the directional derivative itself does not exist, then what
Yeah,
happens?
that's the thing.
Right? I guess in the lecture you have seen this particular function given as the function for which the directional derivative at 0 comma 0 does not exist. Do you remember that from the lecture? So this is a function, the explanation is also given in the lecture itself. If you don't remember, just go back to the lecture and see from week 9. This function is given as an example for which the directional derivative at 0 comma 0 does not exist. It involves just some simple limiting concept only,
Yes.
not
Yeah, they
anything.
took y as mx and then
Yeah, yeah, that's the thing. Y is
simplified
equal to
to
everything.
Two different limits.
Here you are going to use the limit formula instead of the gradient formula. You will be using the limit formula which we initially saw for the directional derivative. Okay. Okay, fine. So here we cannot use the above technique for finding ascent or descent. What are the other possible techniques that we are not going to look into this course? So only to this particular concept where the directional derivative exists, only that part only we are seeing here. Okay, fine. Okay, so now we have seen what are derivatives. So now what is the concept in one-dimensional cases which you see parallelly to derivatives? Even to define derivatives, I guess you use tangents in the case of one dimensions. I don't know how many of you remember how the
Yes,
derivative was defined.
tangents, slope
Slope?
of tangents. Something.
Yes, the slope of the tangent at that point to the curve. That is how you define the derivative at a point, right? So we are talking about derivatives. So next obvious concept which we need to see is the tangents, right? So tangents, first we are looking for scalar valued multivariable function. A tangent line to a curve C at a point P on C is a line which represents the instantaneous direction in which the curve C moves at a point. This is what we see for one-dimensional cases. But many people say that it is a line which touches the curve at that point, right? It touches exactly at that point, right? But is
Yes.
this a correct definition? Is this a correct definition?
No.
No, right? Because if you are taking some curve like this, then if you take the tangent, it is going to cut like this, right? It's going to cut here also. So this definition is wrong. So this is just some intuition. This is just to understand in some specific scenarios. This definition you just forget. Okay. So don't use this traditional definition. This is just an intuition to understand in the very beginning. Now, moving forward, you have to look at this way. It is the direction of instantaneous direction in which the curve C moves at that specific point, right? So now in one variable, you know that the tangent of f at x is the tangent to the graph at this point, right? So for example, if you have a curve like this, then at this point, at this point, at this point, you see these are the tangent lines. And what is the direction in which it is changing? That slope at those points gives the derivative at those points, right? So, and this is the equation of the tangent line in one variable, right? Okay. Now, for example, what is the tangent at this point?
0.
It is this horizontal line, right? Right? You see that this tangent line, in fact, cuts the curve like this, okay? And here you know that the slope is 0, right? So, the derivative at 0 is 0. Okay. So these are just recalling from one variable. Now coming to two variable functions. So first we are talking about f of x comma y, not any multivariable function. So we can visualize first what's going on. We can visualize and then we are going to give the general formula. Okay. So let f of x comma y be a function on a domain D in R2 containing some open ball around the point A. Consider a plane in D passing through A tilde and restrict F to D. Maybe the plane I will call it as L. Okay, this plane I am calling it as L, or maybe plane P. I don't know, point P, or you may be confusing. I guess L is fine. So this is your L. Okay, I am calling the plane as L. Okay, so I am going to restrict this function to just a plane. So this is the whatever you see in this purple color. This is actual function f of x comma y on the entire domain D in R2. Now, instead of considering the entire domain, I am going to restrict this to a plane which passes. So this is your point A tilde, which passes through the point A tilde. Okay. Now, what is the intersection of this plane and this function f of, this is your function f of x comma y. Can you see what is the intersection of this plane and the function f of x comma y?
Black line.
Yes, this black line you see here, this is the intersection of F with L, correct? Right? So now when you are restricting your function to a plane, your function on two variables becomes a function of one variable,
Single
because now one variable, right? Now because you just have one simple curve, correct?
Yes, ma'am.
Yes. So now you can just look at it as a usual one variable curve and see what is mean by a tangent at that point, correct? Yes.
Yes.
Okay,
So
ma'am.
since it is now a function of one variable, we can consider the tangent of f at a over d as above. Okay, over L as above. If the tangent L is in the if the tangent is in the direction of the unit vector, then the tangent will be the line with slope fu at a tilde passing through the point a tilde comma f of a tilde. Okay, so now if this line, okay, if this tangent, okay, is in the direction of u, then this will have slope fu at a tilde. Okay, and it passes through the point a tilde comma f of a tilde. Do you understand from the graph what's going on? Yeah.
Yes, ma'am. We
Oh,
are just putting a constant value, right? At one of its
we are
x.
just looking at what is the tangent line at this point in a specific direction. Okay, so now you are having this point. Now I am considering a considering this particular line. Okay, so if the tangent is in the direction of the unit vector, then the tangent will be the line with slope fu of a tilde passing through the point a tilde comma f of a tilde. Now if I have taken a different plane, I will be getting a different curve through the same point. Do you agree?
Yes, ma'am.
Yes.
Got it.
Then you will be getting the tangent with respect to some other direction, correct? Right? Yes or
Yes, ma'am.
no?
Yes.
Yes. So that is what is happening in case of functions of two variable. Instead of just one tangent, you are going to have several tangents, each of those tangents in some specific direction. Okay. So now you have a formula for this. We are not going into the derivation part of these equations. So in the case of one variable, you have the equation of tangent line like this, right? So here we are also having equations of tangent lines to f. Okay, and here we are not going to look at the derivation part. We are just going to use the equations given to you. Mainly these are the two formulas we are using in general. This we very rarely use. Okay, so for a function f of x comma y, okay, with the domain in R2, which contains a point a comma b, the equation of tangent line to the function at the point a comma b in the direction of the unit vector is given in this way. Okay.
Ma'am, so this A comma B is point where tangent is passing, right?
Yes, yes. It's passing through this point.
So this is
Yes,
A comma B, right?
yes, yes. You can say it is a comma b. Yeah,
Okay.
but here you are considering it as a function of two variables, right? So it is a comma b. But when you are looking at more general place, then you will have instead of a comma b a general point. That's all. The
Okay,
same
got it.
definition we will see for x1, x2, xn also.
Mm-hmm.
Okay, fine.
Okay.
Okay, so now let us use this formula given here to find the equation of tangent at this point in this direction. So can you all use this formula? What is your a and b? Can you tell? For here your function f of x comma y is given. What is your a and b? Can you tell?
1 comma 1.
Yes, your a comma b is 1 comma 1. So if this is 1 comma 1, what is this 1 0?
So unit vector.
U1, U2.
U1
Oh,
u.
yeah.
Now you have this formula parametric equation. Find x of t, y of t and z of t with this formula given here. So everyone do this problem. Meanwhile, we will have a short break. Okay. So everyone use this formula and find x of t, y of t, z of t. I
Ma'am,
hope.
would you
Yes.
please scroll up a bit? scroll up. Yeah, got it.
Okay, let's continue in a few minutes. Okay, I guess you all have completed finding the tangent. So can you tell me what is the tangent? What is x of t? X of
1
t is,
t,
yes, 1 plus t. Y of t is
1
So one.
1.
1,
Z of t is
2 plus
2
t.
plus t. Right. So this is the equation of the tangent. X of t, y of t, and z of t.
Ma'am, can you explain how that z of t is equal to 2 plus t?
What is fu of a comma b? First of all, what is del u? Sorry, del f. Del f is 1 comma 1, right? Del f at del f is first of all del f at x comma y. What is del f at x comma y? 1 comma 1. So at 1 comma 1 also it is going to be same because it is just a constant. Now what is fu at 1 comma 1? Del f at 1 comma 1 dot product with which vector? What is u?
1 comma 0.
So now what is dot product of 1 comma 1 with 1 comma 0?
1,
1. So this is your fu of 1 comma 1, right? Now what is f of 1 comma 1? What is f
2.
of 1 comma 1?
2.
2, right? So you got 2 plus t, f of a comma b plus t times of fu of a comma b. That's all right. Okay.
Okay, ma'am. Okay.
Okay. So do the
ma'am.
next. Yeah.
This equation is in 2D. Why we are calculating in like 3 dimension?
Sorry,
Like
what? Each
x of,
equation is
ma'am, this equation is in 2D, na?
okay.
Then why z like
See, this function is a function of two variables, but then your
oh
equation this tangent is lying in where? In a R3, right? Here you see, right?
yes ma'am, got it.
Mm. Okay. So now do these two problems as well and tell me your x, y, and z. In this case, your u was already an unit vector. But what about this one? What is your unit vector?
3 by 5, 4 by 5.
Yes. You should not forget this step, otherwise your answer will be incorrect. And what is your A and B again?
1
1
comma
comma 1.
Yes. So what is x of t, y of t, and z of t? X of t, y of t, at least you can tell immediately. What is x of t?
3t.
1 plus.
3t.
Again, I told you not to do the mistake. You are doing the same mistake. 3t by 5, right?
3 by 5t.
Yeah. And then y of t is?
1 plus 4 by 5t.
Yeah. And your z of t, what is f of a comma b? 1, right?
Yes ma'am.
Into y. Now, what is fu of a comma b? Find and tell me. So your del f is nothing but y comma.
X.
So del f at 1 comma 1 is 1 comma 1.
Comma 1.
So fu at 1 comma 1 is
1.
comma 1 dot 3 by 5 comma 4 by 5. So 3 plus 4 by 5, 7 by 5, correct?
Yes.
So 7 by 5t, correct? Yeah?
Yes.
Okay, so now do the same for the next problem as well. Find x of t, y of t, z of t. You have the formula here. Now what is your u?
1 by 5, comma 2 by 5.
1 by 5, just 5
Yeah,
or
5, root 5.
root 5, right? So this is your u1, this is your u2.
Sorry, ma'am, can you please explain how we are calculating the U?
What is norm u we are calculating, and we are dividing u, this vector, by not norm u, maybe suppose this is, let's say, v, then u is v by norm v, that's all. So what is norm v? Square root of 1 plus 2 square, 1 square plus 2 square, which is square root of 5, that's all. Here, if this is your v, norm v is nothing but square root of 3 square plus 4 square, so 5. Got it?
Okay, ma'am. Yes, ma'am.
So x of t is, just straight away you can say pi plus
1
1,
plus root 5t.
and then y of t is 1 plus,
1
1
plus
plus
root 2,
5t.
2 by 5.
yeah, and what is z of t, did you calculate?
1, 0 plus
Yes, sir. Your f of pi comma 1 is sine pi, so 0, yes, 0. And what is fu at pi comma 1?
Zero.
Minus 1 minus 2 pi by root 5, is that correct? Yeah. Yes,
Yes,
or no?
ma'am.
So minus 1 minus
Yes,
2
ma'am.
minus 2 pi by root 5. So this is your z of t. Okay. So finding the tangents, at least in 2 variables, we have seen. For 3 variable, exactly the same procedure, nothing different. So tangents for multivariable function. So whenever you are having a function of, why did we see 2 variables separately? For visualizing purpose only. Okay. To understand the concept and visualize, we saw a 2 variables separately, and the same thing now is given for n variables also. Okay. So maybe here you have x of t comma, here let's make it w, this is also w, so that there is no confusion with the z here. Okay, here is z is missing. Now apply the same formula and tell me what is x1 of t, x2 of t, x3 of t, and then w of t. What is your u in this case? First calculate that and tell me.
Minus 1 by 3, minus 2 by 3, 2 by 3.
Yes. So this is your a1, a2, a3. So the formula you need to use is a1 plus tu1. So this is your u1, u2, u3. And then here a2 plus tu2, a3 plus tu3. And then for w of 2, you have f of a1, a2, a3 plus t times fu of a1, a2, a3. Now Quickly tell me the answers.
1 plus minus u t by 3.
Yes.
1 minus 2 t by 3.
Yes.
1 plus 2 t by 3.
Yeah. What is f of 1 comma 1 comma 1?
3.
And what is fu of 1 comma 1 comma 1? Del f is
Y plus z.
Minus 2 by 3.
z plus x
X.
plus z, and then here x
Y
plus.
plus z. Mm.
So you have del f at 1 comma 1 comma 1 is 2
2 comma
comma
2 comma 2.
2. So dot product with this vector will give you f u at 8.
Minus 2 by 3.
So what is that? Minus 2 minus 4 plus 4
4
by 3.
By 3.
So which is minus
minus
2
2
by
by 3.
3. Yeah. So minus 2 by 3. So 3 minus 2t by 3. Right? Is that fine?
Yes.
Yeah. So this example we already have seen that the directional derivative at 0 comma 0 does not exist. We have seen the same example before also. I have given the same in a note. Do you remember? Does not exist. I guess it was somewhere here I mentioned that for this function the directional derivative at 0 comma 0 does not exist. So since it does not exist, okay, the tangents also will not exist. At 0 comma 0 the tangent will not exist. Okay, but remember there is a small catch here. Except in the direction of x-axis and y-axis. When you do the limit, you will understand this. Why, what happens in the direction of x-axis? From the term itself, you will understand. Go through the lecture again. I'm saying go through the lecture, understand this example well. Okay. So this is one example, and here is another example. So this you can easily remember it from mod x. What happens to mod x at 0? At 0, does the direction, does the derivative exist?
No.
No, right? The derivative
No,
does
ma'am.
not exist for mod x at 0. You have a sharp edge. Same way for this function also at 0 comma 0, you can see that the function will not have a tangent. Okay. So these are some examples that the tangent need not always exist. Okay. Okay. Then what is a condition which guarantees the existence of tangent? So if you are having a function from d to d, which is in Rn, right? And you are having a point A in this domain, then you need to first have the gradient to exist and to be continuous. Then for every unit vector u, the directional derivative exists. You know that. So if the directional derivative exists, then the tangent is going to exist, correct? So just in the case of one-dimensional one variable, so the tangent exists if if the derivative exists. Here the tangent exists if the directional derivative exists. That's all. Okay. So and the directional derivative exists for under this condition. This is a condition which guarantees the existence of directional derivative at a till. Already I have mentioned it in this lecture. So the conclusion is that all tangents at a point exist when the gradient exists and is continuous on some open ball around the point a tilde. Okay, is that fine? So this is the condition and which the under which the tangent at a point exists. Okay, fine.
Ma'am, can you repeat this?
See, what is the condition for the tangent equation itself? You see that a and you are going to have automatically. These values are not going to be a problem. F is defined at a, in fact, that is something we are assuming from the beginning because it is there in the domain. Now, what is the one thing which we need to think about in the equation of tangent? This is the only thing. If this exists, then the equation of the tangent is ready for us. It means the tangent exists, yes or no? Right?
Yes, ma'am. Yes, ma'am.
So
Got it.
we need the directional derivative to exist. And the directional derivative exists under this condition. That is why we are saying the tangent that exists at a point exists when del f exists and is continuous at the point. You understand now?
Yes, ma'am.
Okay, fine. So now I told you, if you remember from the graph, if you are taking a different plane, then you are going to get a different tangent. Like this, you are going to get several tangents for the same point. Now all these tangents, okay, all these tangents are going to be lying on one plane. Okay, and that plane is called the tangent plane. So for example, I have taken two different directions and got two different curves, and I have taken the two tangent lines along those two different directions, and I have built the plane from those two directions, because for a plane, you know that two vectors are sufficient to build a plane, right? So I have got the plane. So the equation of the tangent plane is given in this way. Does it resemble something? If you go back, what is the equation of the tangent we saw? If I rewrite this, this is y is equal to f of a plus f dash of a into x minus a, right? Now just let's look at the equation of the tangent, right? You understand the similarity, right? You can see the similarity, right? So this is the equation of the tangent plane. Okay, is that fine? So here also again we are just having the equation here. We are not looking at the derivative part, just we are looking at the equation. Okay, fine. So for these examples, find the tangent plane. So this is the formula, everyone, you can write it down. Z is equal to f of a tilde plus del f of a tilde dot x minus x tilde minus a tilde. So find the tangent plane. Maybe here also instead of z, I will put w only. Again, you may confuse with the z in the equation of f. So the formula is w is equal to f of a tilde plus del f of a tilde dot x tilde minus a tilde. So this is your x tilde. This is your a tilde. Find the answer. Find the tangent plane. Yeah? What
2,
is, yeah? 2,
2 plus x minus 1, comma y minus 1.
not comma. You missed something, I guess. There is a dot product here. So you get a number here. Or you just get,
X plus y minus 2.
yes. So you simply get x plus y and then minus
Minus
2
2.
or plus 2. Yeah,
Minus 2.
plus y, yeah, 2 plus x minus x plus y minus 2. So this is w. How many of you got this answer? So here del f is nothing but 1 comma 1, right? So del f at 1 comma 1 is also 1 comma 1. So del f dot x tilde minus a tilde is del f dot,
X minus 1 comma y minus 1
so x minus 1 plus y
plus y
minus,
minus 1.
so x plus y minus 2. So this is this side and f of a tilde is 2. So when you simplify this, what is that you are getting? X plus y minus w is equal to 0. Right? So this is the equation of a plane in R3. If you think that you have x, y, instead of z, it is, the name is just w, that's all. In R3, what does this represent? What does this equation represent in R3?
A plane.
Yes. Right? Okay. Similarly, do the same problem for this function. Find the tangent plane. Yeah. What is f of 1 comma 1? Simply.
1.
And your del f is y comma x. So del f at 1 comma 1 is
1 comma 1.
1 comma 1. So del f dot x tilde minus a tilde should be x tilde minus a tilde is x minus 1, y minus 1 again. So I will get the same,
X plus y minus 2.
right? So you will get w is equal to 1 plus x plus y minus 2. So you are going to get x plus y minus w
Minus 2.
is equal to 1, right? Equation of another plane. This plane passes through origin and this does not pass. That's all. Both are planes in R3, right?
Ma'am, PA solution is not available in that drive, ma'am.
PA solutions are there in the form of videos.
PDF not available, ma'am?
No.
Why, ma'am? Other subjects are available PDF. Why Maths 2
For
is?
PA.
Yes, ma'am. PA practice assignment.
Okay, let me check. I usually, I don't know. You for GS we are giving PDF. For PA, okay. Let me check and if necessary, I'll add it. Okay.
Please add it, ma'am.
Yes, yes, yes.
Okay, thank you.
So those who have completed the previous one, do the next one. So what is f of 1 comma 0?
Sine 0.
What is that?
0.
Yeah.
0.
Now what is del f?
Y cos xy. X cos xy.
And del f at 1 comma 0?
0 comma
1.
1.
Okay. So the next step is what is del f at 1 comma 0 dot product with x minus 1 comma y.
0
Just
comma
y.
0 comma okay. Dot okay. 0 plus
Okay. So now what is your tangent plane then? 0.
0
Plus
plus
y.
y.
Right. So you have y minus w is equal to 0. That's all. Okay. So next you have a function of 3 variables. So the same process only. What is f of 1 comma 1 comma 1?
3.
What is del f?
y plus
Z.
comma y plus z.
X plus z. Y plus x.
del f at 1 comma 1 comma 1 is
2 comma 2 comma 2.
so del f at 1 comma 1 comma 1 dot product with x minus 1, y minus 1, z minus 1, which is
2x plus 2y plus 2z minus 8.
so 2 times of x plus y plus z minus 6, right? So now what is your w then? 3
Plus 2x yz minus 6.
Ma'am, can you explain why you multiply x minus and y minus? And actually, I'm not there at that time. Can you explain it? Uh,
this is nothing but x tilde minus a tilde. So this is your x tilde and this is your a tilde. What is x tilde minus a tilde?
okay, got it. Thanks.
Yeah. Okay, I guess now you are very comfortable. So maybe the next problem I will give it as a homework. Okay. So do this as a homework. This is a very simple one. Okay. Linear approximation is a concept which is almost same as tangents. It is not anything different. Just the terminology is different. Just the name is different. It is exactly the tangent only. Okay. So for example, if you are having a curve, what is the linear approximation of this function at a given point? It is nothing but the equation of the tangent line at that point. Okay. So the same thing if we are asking in case of Rn, then we are going to tell about the tangent plane. Okay. Let me repeat. If you are having a curve and you are asking what is the linear approximation, linear means it should be a line or it should be a plane, something like that. So in those case, you see in case of one variable, you see that this curve, the linear approximation is given by the tangent at that point, the equation of the tangent at that point. In case of Rn, it is going to be the equation of the tangent plane at that point, right? So now, what is the linear approximation to this function at 1 comma 1? Do we already know the answer?
Yes.
Yes. So what is that? We already have computed, right? What is that?
X plus y minus w equals to 1.
Right? We have already computed. So this is the linear approximation to f of x comma y. Okay. Now this one you will know once you complete this. So this is also a homework. So linear approximation is the same concept as tangent, just the name is different. Is that clear for everyone?
Yes, ma'am.
Okay, fine. Okay. So the next topic is what are critical points? Okay. So in first, let us recall for functions of one variable. So for functions of one variable, a point A is called a critical point for a function f of x if either f is not differentiable at a or f dash of a is 0, right? So if f is differentiable at a point A of local extremum, it satisfies f dash of a equal to 0, and so every point of local extremum is a critical point. Okay. So what does that mean? So let us consider this graph. So for this graph, at which points do you think you will have f dash of a 0? So
Where the local maxima and minima are.
yeah, so for example, maybe some point here, this point, you see, right?
Yes, ma'am.
This point is a local
Minima.
Minima.
minimum. And what about maybe this point?
Local maxima.
Maxima.
Okay. What about this point?
Local minima.
Okay. So I guess everyone knows what is local maximum and local minimum. In a neighborhood, in a given interval, if that point is the least or highest, if it is least, it is going to be local minimum. If it is the maximum, then it is going to be the local maximum. Okay. So this is local maximum and local minimum concept. Now there is something apart from local maximum and minimum where the derivative is again 0. At these points, you can also notice that the tangent will be parallel to the x-axis, correct?
Yes, ma'am.
So the derivative is 0 at these places. Okay. There is another possibility that your f dash of a is 0, but it is neither a local maximum nor a local minimum. Those points are called saddle
Critical.
points.
Okay, settle.
Okay. So saddle point is a critical point which is not a point of local extremum. Okay. So your derivative exists and it is equal to 0, but it is not a local extremum. For example, if you consider f of x is equal to x cube, how does the graph look like?
Ma'am, in this graph itself, we have a
Yeah,
locus.
yes. So this is a usual function example we give. Yes, you can see here also. Here you are seeing that it is going like this. Here you can obviously see it even better. So it's going to be something like this. Okay. So at 0, passes through 0 exactly. Okay. So here the tangent is exactly the x-axis itself. Okay. But this point is not a local extremum. Neither a local maximum nor a local minimum, right? You can clearly see that. To the left, all the points are having values less than 0. And to the right, all the points are having greater than 0. So there is no interval in which this point is maximum or minimum, right? So this point is called a saddle point. So what is a saddle point? Everyone understand, right? Yeah.
Yes.
Why the name saddle? Do you know what is exactly a saddle? I mean, non-mathematical saddle. This is a saddle where you sit on a horse, the seat, kind of a seat you have, right? This one. This is a saddle. Okay. And why we are using that here? Okay. So the saddle side view is here, the front view is here. From the front view, the middle point, this point. Okay. This point, when you are looking at like this is on the top, correct? It is on the top of this curve. Now, when I'm turning the saddle in the sideways, now the same point is at the
Minima.
bottom of this curve, correct? So you see that along this direction, you see the point is on the top, and along this direction, the point is at the bottom. So it is neither a maximum nor a minimum. This is a saddle point. Okay. So in case of several variables, you can see, for example, you take this curve. Along this curve, right, this is a minimum. But along the blue line, the same point is a maximum. You all can understand, visualize that? Yeah. Along this orange line, you can see that this point is minimum. But along the blue line, this point is maximum. Can you
Yes.
visualize that? Yeah.
Yes, ma'am.
So such points are called saddle points. Okay. Fine. So local extrema for multivariable functions. Let f of x still be a function defined on a domain D in Rn, and suppose there is a point A tilde in the domain D. Then that point is a local maximum. What is the definition? If there is an open ball containing A tilde such that inside this open ball, f of x tilde less equal to f of A tilde. Okay, fine.
Yes, ma'am.
Okay. And the same goes the other way around. If the inequality is reversed, then it is local minimum. So if a point is either a local maximum or a local minimum, we generally common term for both of this is local extremum. Okay. So if del f of A tilde exists for a local extremum, then del f of A tilde should be 0. Okay. So how are we going to define critical points for several variable functions? Again, the same. First of all, either the gradient function does not exist or the gradient function exists and it is equal to 0. Okay. So instead of the derivative in case of one dimension, we are having the gradient function here. Okay. So now can you find the critical points of this function? What is the
Ma'am,
first step? Yes.
why this equality hold? Can you just scroll down?
This one.
No. Little bit scroll down. Yeah, this. Local maximum. Yeah, this inequality.
This one.
Why this equal f of x is equal to f of a? Then what it mean?
See, you are just taking some interval. For example, this point I'm taking. I'm considering one interval here. Okay, this is your open ball now. Okay, this interval is your open ball. Now,
Okay.
for take any point x here. Okay, so then let's call this point as a. So your f of x, take any point, f of a is less equal to f of x for any points in B. So this B contains your A as well. So at that point you have A, f of A equal to f of A. Okay, fine.
But this equality count in both way, right? In local maximum and local minimum
This
also.
is for local minimum, it is this way. And for maximum, it is the other way around. So for maximum, f of x should be less than the value. So for minimum means this is the smallest. So other things are bigger. For maximum means this should be the
Okay.
bigger value and the other values should be smaller. Correct?
Okay, ma'am.
Yeah. Okay, now to find the critical points, what is the first step to find critical point of a function?
To see if
Find,
it exists.
Differentiate first.
find del.
Del.
First find del f. What is your del f?
2x
Ma'am,
plus
2x plus
y
6 plus 2.
And then
6x plus
8y
8y minus 4.
minus 4.
okay. Now your second step, equate del f equal to 0 and solve. So if you put del f equal to 0, what will you get?
Madam, directly can't we find fx equal to 0, fy equal to 0?
Yes, of course, that is what we are doing. Instead of writing fx, fy, I am writing del f. That's all. That the same process only. Nothing is different.
Okay.
Ma'am, y equal to minus 1.
Y is equal to minus 1 and
2. X equal to 2.
so what is your critical point here? 2 comma minus 1. Okay. Did you all get the same answer?
Yes,
Check
ma'am.
it.
Yes, ma'am.
X is equal to 2, y is equal to minus 1.
Okay, fine. Okay. So saddle points again for multivariable function is a critical point A such that del f of A tilde exists and del f of A tilde is 0, but it is not a local extrema. Okay. So here you see this point is a saddle point and this point is also a saddle point. Okay, fine. So I will just give the definitions of absolute extrema. We are not having time for doing problems. I'm just giving the definition of absolute extrema. Okay. So let f of x tilde be a function defined on a domain D in Rn and suppose you have A tilde in D. The point A tilde is an absolute maximum or global maximum of f. If f of x tilde is less equal to f of A tilde for all x in D. What is the difference between local maximum and local minimum? Here you are having for all x in this ball D intersection D, the intersection of the open ball with the domain. Now here you see that you are having x tilde from all the domain. So suppose let us say your domain is minus 5 to 5. Okay, this is your domain, let's say. Okay, now I am, let's say this is minus 5 to 5. Okay, just roughly I am going to draw some graph. Okay, so now I'm taking this point as A, this point as B, C, D. Now which of these points are local extrema or local minima, local maxima, you can say A, B, C, D. What is A? Is it a local maxima or local minima?
Maximum.
No.
Local maxima. And is it also absolute? In
Yes,
this
ma'am.
domain,
Yes, ma'am. Yes, ma'am.
and absolute as well, and absolute maximum. What about B?
Local minima.
Local minima.
Is it absolute?
No.
No, ma'am.
No, because in the whole domain there is a value which is having,
D.
yes. So D is local minima as
Local.
well as absolute minima. What about the point C?
C is
Local
Local
maximum.
maxima.
Yes, but it is not absolute. Okay, you understand the difference between local and absolute, right? Okay.
yes.
So now you look at such graphs. For such graph, so now for this graph, do you think there is a global maximum?
No, ma'am.
No.
But you can see that there is a global minimum. Okay. Now you see another function. For this, you see that global maximum is there, but minimum is not there. Okay.
Yes, ma'am.
So sometimes if you are asked to find global maximum or minimum for functions like this, so for which you the graph is very simple, at that time don't spend too much time. So if you are having x squared plus y squared, you know the graph, and so at 0 comma 0 you have global minimum. Okay, fine. Okay, so here we have the process of finding the absolute extrema. I guess it will be beneficial only if you do a problem following it. Otherwise, just giving the steps will not make any sense. So maybe shall we wind it up with this, so that only this topic is remaining in week 10. We have covered everything else in week 10. So can we do this in the next session then? The process of finding absolute maximum and minimum. Yeah.
Yes,
Yeah.
ma'am. Yes, ma'am.
Okay. So in this session for week 10, in week 10 content, first of all, we have seen what is steepest ascent and steepest descent, and how to find the direction of steepest ascent and steepest descent. This we did using directional derivative, right? And then what is the next thing we have seen? After doing that, we have seen the concept of tangents.
Tangent.
Tangent.
Yes, tangents we have seen, and then we saw the equations of tangents, and then we moved to tangent planes, right? And we saw that tangent plane has another way of calling it. What is that name?
Linear approximation.
Linear approximation.
Yeah.
Okay. After this, doing all this, then we move to what are critical points. So in critical points, we saw that a critical point can be either a local maximum, local minimum, or a saddle point, right? And if given a function, how to find the critical point? Find the gradient, equate it to 0, solve it, and you get the critical points. Okay,
Okay.
fine. So these are the things we have covered in week 10. So in the next session, you can look at absolute maximum, absolute extrema of a function, and whatever
The extrema and the maximum both are same, but just terms are different.
extrema includes both minima and maxima. That's all.
Okay, ma'am.
Okay. So only one thing I wanted to tell. See, this week we are having the session on Wednesday instead of Thursday, because the deadline for week 10 is on Wednesday. So I have made the session on Wednesday for your convenience only. So on Wednesday you can see the remaining topics.
Okay,
Okay,
ma'am.
fine.
Please share this PDF.
Yes, I will share it. Okay, then thank you everyone.
Thank you,
Fine.
ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.